Hello there and good evening and welcome to you all to the Catalan Cymru revision sessions. The session this evening will focus on AS Further Maths and will be presented by Mr Matthew Macmillan. Matthew Macmillan is a teacher at Christ College, Brecon, and we welcome you to our session this evening. The session will last around 45 minutes, where Mr Macmillan will run through the relevant content. If you have any questions during the session, please use the question and answer section, and we'll do our best to answer your questions during this evening's session. You will see that there's a hyperlink in the Q&A section. If you're happy to leave your name and email address, we would love to keep in touch with you so that we can send you information about any future events. You can click on the link at any time during tonight's session. Today's session will be recorded, and the recording and any relevant resources will be uploaded to the e-sgol website under the Catalan Cymru tab. For now, Mr Macmillan, over to you.
Okay, thank you very much. So this is the second session. I'll just move forwards through the slide to remind you what we did last session. Last session we did some pure work, and we're continuing with some pure work this session, and then next week we'll do mechanics and the following week statistics. So I decided to look at complex numbers and vector geometry today. If we have time, we'll look at the roots of a polynomial, but that's only if we have time. We might run out of time. We'll see. So starting off with complex numbers, the advanced information given by the WJC is highlighted in yellow, and there's a few interesting things. If we just look over here, for instance, on the left hand side, it seems like there's highly likely to be a quartic equation that you have to solve in there somewhere. Over on the right hand side over here, they're suggesting that we don't need to know modulus argument form, although that is something I am going to cover, because if you don't need it in year 12, you definitely will need it in year 13. So these are really a guide from the exam board, but I wouldn't necessarily say, oh, I shouldn't revise or learn that. I'm going to try and cover two parts of complex numbers. So if we just scroll forwards, the first part is just looking at basic operations involving complex numbers, and then I'm going to look at some transformations involving complex numbers. So the complex number given here, 2 minus I, and then it says we've got a complex conjugate denoted by this symbol. You might use different symbols. You might see a Z, for instance, with a little star next to it. There are various symbols used. They seem to be using this symbol. So the complex conjugate here, that's just where we change the symbol in the middle. We change it to a positive, or if it started off as a positive, we're going to change it to a negative. A little trick that I have seen in a past paper is where they gave the complex number looking like this. For instance, 3i plus 5. And then the complex conjugate, you need to be careful there because it's the imaginary part that we're changing. So the complex conjugate here would be negative 3i plus 5. Just watch out for that little trick. I'm just going to put a cross through that because that's not related to this question. So for this question, let's copy it down. Z minus 5 conjugate over Z. We are basically replacing the Z for 2 minus I, and we're replacing the conjugate for 2 plus I, all over 2 minus I. Now, this here is something I'm just going to take over here and do a little bit of work on. Basically, it's a bit like rationalising the denominator when you have a surd. So I'm going to copy this bit over here, 2 plus I over 2 minus I. And if we multiply this by the conjugate of what's on the bottom, so we're multiplying it by 2 plus I over 2 plus I, like that. Multiplying this out, so on the top we're getting 4 plus 4i plus I squared. And then on the bottom, we're getting, well, 2 times 2 gives us 4. And I guess the 2 times the positive I and the negative I times the 2, they're going to cancel each other out. And then the negative I times the positive I is giving us negative I squared. Now, with your I squareds, well, I to the power of 1 just equals I to the power of 2 gives us negative 1. I to the power of 3, that's going to give us negative I. And I to the power of 4, that's going to give us 1. Really, this year, we're only looking at that one, I squared, but next year you might investigate this a little bit more. Let's continue, because I haven't quite finished tidying this bit up here. So because that I squared is equal to negative 1, oops, we're actually getting on the top here 3 plus 4i over, and then this bit on the bottom here is negative 1, so we're getting over 5. Now let's put that back into the left-hand side over here. So we're getting 2 minus I minus 5 times 3 plus 4i over 5. So that's what I've got when I've dealt with that green bit. It looks like the 5s cancel, which is why I didn't take it over to the left-hand side, to the right-hand side. So they're going to cancel off. And then we're left with 2 minus I minus 3 minus 4i. Because we have a subtraction here, be careful with that bit. That gives us negative 1, negative 5i. We haven't quite finished because this is saying find the modulus and argument. They might not go this far in the actual exam, but we will continue with this. So the modulus, basically on the right here, I've got the complex number here. So this is minus 1 and this is minus 5. This is our real axis and this is our imaginary axis. So this is how we represent this on an Argand diagram, minus 1, minus 5i. Modulus is basically saying how long that line is. So the modulus of minus 1, minus 5i, we're going to take each number, square it, add them together, and then square root it. That's root 26. A surd would be acceptable here. So the length of that line is root 26. For the argument, that's the angle that we're getting. We just want to be careful when we get this angle. So the argument is, imagine that you start off pointing in this direction. How far do I have to turn there? That's the argument. Or it could be that you turn the other way and you could say I'm going to go negative, in which case you'll get a negative angle going that way. Different examples might prefer it in a different way. To work this out though, we're actually going to work out this bit here, and I'm going to call that theta. And I think about the opposite, that's 5, and the adjacent is 1. So theta is the inverse tan of 5 over 1, the opposite over the adjacent. That's 1.37 rads. In fact, I'll put radians just so that you're happy with that. And then because I actually want the red angle here, the argument of this complex number, minus 1 minus 5i, we need to add on 180 degrees. Because I've used radians, I should use pi. So I'm adding on pi. And that's 4.41. I think in the mark scheme for this question, they actually allowed it in radians or degrees, but just make sure you read the question. So that's how to deal with the, it's basically this bit, making sure that you can deal with rationalising the denominator here. An additional type of question that I've seen, and this might be something that comes up this year. I'll just flick it forwards. Is a question like this. We've got a complex number and the complex conjugate, and it says it satisfies this equation. What you need to do here, and I'm not actually going to do this one, I'm going to set it up so that you can have a go at it yourself. For this question, you need to set up Z as a real part and an imaginary part, so x plus iy. That means the conjugate is going to be x minus iy. You should expand the right hand side, and I guess you'll have to do a little bit of expansion over here on the left hand side because it's going to be 2 multiplied by everything here. Then you'll take the real parts and make them equal to each other, and you'll take the imaginary parts and make them equal to each other, and you should get some simultaneous equations. You then solve them to find x and y. You might want to pause the video now and try that yourself. And then on this next slide is the solution, or the mark scheme. Now, if you'd like an extra question on complex numbers, this is the one I thought you could try, where you're doing very similar to what I've just done in my worked example. To find it in the right form, it's going to involve rationalise the denominator here, where you've got 1 over z. And then on this next page is the mark scheme for that question. Now, moving on to a question involving a transformation. These ones are trickier. They're probably more towards the end of the paper because they do think they're a little bit trickier. So the complex numbers z and w are represented by these points. And it says respectively, so this one at the top here, first one is z, and that is equal to x plus I y. So I've got that from here. The next one is w, so w equals u plus I v, that's this bit here. And then we've got some kind of expression that links them down here. It says obtain expressions for u and v in terms of x and y. So I'll just copy the equation down. W equals 1 over 1 minus z. And I've just written down what w and z are at the top. So I'm going to put them in place. So w was u plus iv. And z is x plus I y. So that's the first step, replace the w and the z for the complex number that they represent. Now, if possible, you want to try and keep the, because it's sort of talking here about obtaining expression for u and v in terms of x and y, you want to keep the u and the v on one side and the x and the y on the other side, if possible. So let's just continue here. Now, I'm going to just tidy this bit up at the bottom here. So this is 1 minus x minus I y. And I'd like to visualize this as kind of the real part of the denominator there, plus the complex, plus the imaginary part here. What I'm going to do is rationalize the denominator. So I'm going to take the whole lot here and I'm going to multiply it by the complex conjugate. So it's still 1 minus x, and we've still got an I y, but the negative is going to turn into a positive, and we're going to do the same to the top. 1 minus x plus I y. So we'll keep going. On the numerator, we're going to get this 1 minus x plus iy, because you're just timesing it by 1. The denominator, so I'm looking at these two bits multiplied together. That's giving me 1 minus x squared. Feels like it's going to get quite horrible when I try to multiply this bit here by this bit and vice versa. But the whole point of multiplying by the conjugate is that those bits are going to cancel each other out. So really, I'm only interested in multiplying the minus iy by the positive iy here. So that's going to give me negative I squared y squared on the bottom. So that gives me 1 minus x plus iy on the top, all divided by 1 minus x squared. And then the I squared is minus 1, so we just get plus y squared as the denominator. Now I'm just going to do a little bit more over here. We then take the real parts and the imaginary parts and we're going to compare them. So the real parts, well, it's the u on the left hand side, and on the right hand side the real bit is 1 minus x all over the denominator 1 minus x squared plus y squared. So that's the real parts dealt with. So we've got an expression for u in terms of x and y. For the v part, we're just comparing the imaginary bits. So the imaginary bit here, I don't want to include the I, it's just the imaginary part of it. So it's v equals, and then it's, I don't want to include the I here, it's just the y over 1 minus x squared plus y squared. So that's that bit dealt with. Now for part B, and this one is a little bit tricky. I'll show you a visualization of this in a moment. So point P is moving along this line, and we want to find the equation of the locus of Q. I'll just copy this down. Y is equal to 1 minus x. So my way of doing this is thinking, let's change anywhere we've got 1 minus x, for instance, here and here. Let's change them, oh, and here. Let's just change them into y's and just see what happens. So u is equal to, so I'm changing the 1 minus x to a y, and on the bottom I'm changing that 1 minus x to a y. So that's what we get for u. So that's y over 2y squared, or 1 over 2y. Let's do the same with v. So v equals y over, and the 1 minus x is y, so it's y squared plus y squared. Oh, this is starting to look very much like the left-hand side. Let's just continue. So y over 2y squared. So v equals 1 over 2y. You'll notice that they are the same. They're equal to the same thing. So that means that u must equal v. Therefore, u equals v. That's the equation of the locus. Let's have a look at what this is actually doing. So if we kind of imagine this bit here as like imagine an axis that looks like that. It's crossing at 1 and it's got a gradient of -1, so it must be a line kind of heading down roughly like that. The other one here, this is, well, it's just a diagonal line, isn't it, going through the origin, kind of like that, u equals v. Let's put them together and we'll just have a look at this visualization. Hopefully it works. So I think I just need to change the equation in here slightly, because that's not what the equation was. It was 1 minus that. If I click play now, you can see the coordinate here. That's the equation that we had. That's y equals 1 minus x. It's got a gradient of -1. It's crossing the y-axis at 1. This point w, that's what the locus of points is going to be for my new equation. So if I click play, you'll sort of see it create the line. Well, it should be y equals x. It's obviously u equals v because it's kind of using a different set of axes, but they're overlaid on top of each other here. So this is the situation that we have. I'll put a link to that in the Q&A if it works. There it is on the PowerPoint as well. Now, what is interesting is you can change this bit just a tiny bit. If I zoom in and out, it refreshes it. You can change this bit just a tiny bit. So if we change this back to what it started off as, it feels like it's not going to draw too different a shape. If I start playing this now as an animation, we actually get a circle. And you can draw lots of other different shapes. This is also quite a common exam question where you get a circle popping out. Let's see if I can work out how to head back to the PowerPoint. Hang on a minute. There we go. We haven't actually finished the question because we've still got part C to do. I'll do it here. Find the coordinates of the points in the Z plane which are transformed to points in the same with the same coordinates in the W plane. So that means my Z is still going to Z. The X and Y coordinates will be turning into the same X and Y coordinates. So in the equation here, I can just replace that for a Z. Z equals 1 over 1 minus Z. If we rearrange this, we get Z times 1 minus Z equals 1. If we expand the brackets and make the quadratic positive, we get Z squared minus Z plus 1 equals 0. When you go ahead and solve this, and I would show your method for solving this, so you'll be using the quadratic formula, you're going to be getting Z equals 1 plus or minus the square root of root 3 all over 2. That gives you your two solutions. So Z equals 1 plus I root 3 all over 2, or Z equals 1 minus I root 3 all over 2. These aren't quite coordinates yet, so the coordinates that you're getting are the real parts and the imaginary parts. So the coordinates are 1/2 and root 3 over 2, and 1/2 and negative root 3 over 2. Okay, so that also does pop up sometimes. Now on the next slide, here's a question that you can try yourself. And then on the next slide is the mark scheme for it. Now there's one extra thing that I just needed to show you to cover the whole sort of spec points that do pop up here, and it is a part that they have suggested with the advanced information. It is suggested that it's going to be in there. Construct and interpret simple loci in an Argon diagram. So I've kind of put the three that you might encounter, or that I feel like you might encounter. We've got a circle on the left-hand side. If you do follow the links, in fact, what I'll do is I'll follow the link. These are published by Pearson. So you can kind of move your, when it loads itself up, there we go. You can kind of move the circle around using the sliders. You can move the radius. It's basically saying that the modulus, so the distance from the centre to this point out here, must always remain constant, and that's kind of how we're defining this. I'll post the link to the circle just in the Q&A. And if I get the other one up. So the other one is a half line. Again, you can play around with that if you like. I'll post that here as well. And then the final one, which I'm just going to talk about and give a bit more detail on, is the perpendicular bisector. So for this one, I'm not going to do the whole question, concept, because it's stuff you should have learnt already. But the idea here is that the modulus here, you can take, if you're really struggling to remember it, remember Z is represented by X plus I, Y. And we're doing the modulus of that, -2 minus 4I equals, and then we've got the modulus of X plus I, Y, -10 minus 2I. Take all the real parts, so we're going to get X minus 2, and combine all the imaginary parts, so that's Y minus 4I equals, and again do the same over here, so we've got X minus 10 plus Y minus 2I. Now, the modulus means that you're going to square the real part, square the imaginary part, and then square root them both. So we're getting X minus 2 squared plus Y minus 4 squared equals X minus 10 squared plus Y minus 2 squared. We should, technically I should have a square root symbol there, because that's what the modulus is, but you can see, because you've got the square root on both sides, they are going to kind of cancel each other out. You would then go ahead and multiply out your brackets here, and I think if you do this, you should get, well, the equation of this line here. Just be careful, if we look at the specification here, they've kind of put an extra 2 in front there. So if you could imagine that I put an extra 2 in front here and an extra 2 in front here, you'd still have this extra 2 in front here. But when you went ahead and you squared this side and you squared this side, you would also need to make sure you square that 2 in there. Otherwise, it's all going to go wrong. So that 2 will turn into a 4. Now, here's the link to this one. You can see, again, we're saying that we want to keep the distance to this point constant. That's how this is working, and you can fiddle around with the X and the Y coordinates of each point and move them around. So I'll put that again in the link. That might be useful if you're actually doing an exam question on this to check your understanding. Now, on the next page, here is an exam question, and I did specifically choose one here where we have got that situation with the 2 in front of it. So you just need to be careful of that, because it's probably not going to give you a perpendicular bisector. The next page is the solution, and you can see it's this stage here where we've got the 4 has appeared, and that's how we're going to be popping out with the circle. Now, moving on. So next topic we're going to look at is some questions involving vectors. So these are the things in yellow that they're suggesting could come up. It does say some stuff here that I think we just need to be a little bit careful of. Calculate the scalar product, for instance, isn't highlighted, but I would assume we would need that for certain questions. So again, I'm going to try and cover most of this. I think I will pay particular attention to this bit, the perpendicular distance from a point to a line. That seems to be something they are suggesting would be in the exam. Now, on the top here, we have the equation of a line in vector form. You need to be able to convert it to Cartesian form, and I've done that on the right hand side, so you might need to go away and revise that, but you can see, well, do you see the 7 here has turned into a -7 here, and the -1 here is remaining as a -1 there. How the vector equation of a line works is this vector is a single point. So you kind of jump onto the line, and that's what this is doing. This here is the direction, so that then takes you along the line in a certain direction. If we look at this GeoGebra, it shows it quite nicely. This is presented by someone else. Just wait for it to load. There we go. So we have this line. You can see the point P here. The vector equation of the line is given down here. All the stuff above it is the mathematics to create the vector equation of the line. As I change lambda, this number here, it's going to move where I arrive on the line. If I change this lambda to 0, it should take me, oh, if I can get it to 0, it should take me to point A, which is this point here, 2 minus 3, 5. So when lambda is 0, it takes you there. If you put lambda, you know, as 1, 2, 3, etc., it's just going to move you in that direction. If you take lambda back as a negative, it's going to move you in the other direction. There are a few things to note on the vector equation of a line. The first part of your vector equation, so this bit here where my mouse is hovering, that is just any point on the line. So that could, there's loads of answers, isn't there? There's going to be a lot of positions on a line you could put there. The other point is that this here is a vector in the direction of the line. So it could be a multiple of this. We could change all the numbers here. We could change the sign on all of them. So I could turn that to a +5, -3 and +1. So you can get an answer that looks very different from the person sitting next to you in class, and you could still both have the same vector equation of a line. Let's just head back to, in fact, I don't know if I posted that in the Q&A, so we'll just do that. Let's head back to the PowerPoint and just have a look at the vector equation of a plane. So this here is the vector equation of a plane. Now, again, it's very similar to the vector equation of a line. You have a single point, which is this first bit, and these two are directions on the plane. There is something critical here. They cannot be parallel. I think if they started asking you a question about these two being parallel, I think it'd be a bit mean. It's quite a sort of it's a concept that's going into quite a lot of detail, but they shouldn't be parallel. You can also get the vector equation of a plane in scalar product form, where the vector here is the normal vector, and then to get your number here, we do the dot product of a point on the plane. So, for instance, this could be a point on the plane times the normal vector. We'll have a look at an exam question involving this in a minute. I'll just bring up the GeoGebra for the equation of the plane. And again, I'll post this as a link in here. So when this thing loads up, we have got our plane here, and you've got the vector equation of the plane is down here where my mouse is hovering. If we change, probably makes most sense if we change these actually to 0 to start with. So I'm going to move that to 0, and I'm going to move that to 0. That should take us to this point, 2 minus 3, 5. So that's where we are in three-dimensional space. If I change just the lambda value here, I should move along. Which one's representing lambda? I think it's vector B. So I should move along the red arrow. Oh my goodness, I'm getting completely confused here. There we go. Let's make it look like that maybe. Oh no, I think we're underneath it now. Let's see what happens now. So if I move lambda now, you can kind of see it's moving along arrow B, so it's moving in the direction of vector B. If I bring that back to 0, if I move the other one, it should move it along in the direction of vector C. So this is now it moving along in the direction of vector C. If I do a multiple, if I do both at the same time, that should allow me to enter anywhere on the plane. So I'll change that one. I could move this one here. I'm now somewhere else on the plane in three-dimensional space. So the combination of both of those allows me to access anywhere on the plane. Let's head back to the PowerPoint and try an exam question. The Cartesian form of a plane is nice and straightforward. You can basically substitute x, y, and z where it says r, and then you get to do the dot product of that and the normal vector. Right, an exam question. So, it's only 2 marks for this first bit. We've got this plane, we've got the normal vector, and we've got a position vector on the plane. Find a Cartesian equation of the plane, and usually they use a capital pi for the plane. So we are going to do, our plane, which is r dot, and it's times the normal vector, 3 minus 1, 2, equals, and we're going to multiply a point on the plane, so 5, negative 3, negative 4, times 3, negative 1, 2. We're going to use the dot product to multiply out this right hand side, so I'll just kind of do that over here. We should be doing 5 times 3, add negative 3 times negative 1, add negative 4 times 2. If you do that, you get 10. So we have created the vector equation of our plane. It's r, 3 minus 1, 2, equals 10. Haven't quite finished because it says it wants a Cartesian equation. So what we're doing is we're saying that r is an x coordinate, a y coordinate, and a z coordinate, and we're multiplying it by 3 minus 1, 2, and that should equal 10. You are then going to use, a bit like I did up here, you're going to use the dot product multiplying x by 3, y by minus 1, and z by 2. That gives us 3x minus y plus 2z equals 10, and that's our answer. Now, for part B, let's have a look at this. So we've got a vector equation of a line given, and it says it intersects the plane at point x. Show that the acute angle between the plane and the line is 21.2 degrees, correct to 1 decimal place. So it's quite hard thinking in 3 dimensions because this is all happening in 3 dimensions. It might be nicer or might be easier if we try and think in 2 dimensions. So I'm sort of going to think of this as the plane. So that's the plane. And this is kind of looking just at the cross section of the plane. I have got a normal vector cutting that plane. So my normal vector is looking a bit like that. And that's the normal vector. And because it's normal, that means it's at right angles. And then we've got this line. And the line, I don't know where it's going, but it's traveling in 3-dimensional space. But we can kind of imagine that this line, oh, that's not particularly well drawn, could look like that. So that's our line. Now, this point here, oops, it actually says that is point X. So we kind of want to find this point here. I'm going to call it alpha. What we need to do to allow us to do this is we actually are going to start by finding the angle in here. So this angle here, theta, that's the angle that we're going to try and find. How are we going to do that? Well, we already know the normal vector and we know the direction that that's traveling in because it's given up here. What we want then is the vector that's in a direction of L. So that vector there gives us the direction of L. I'm going to call that, I don't know, let's call that B. So if I take B and get the modulus of B, so -1 squared, add -5 squared, add 3 squared, square rooted, that's 35. If I do the same for the normal vector, modulus of the normal vector, that's root 14. Then we're using the fact that the scalar product of the two vectors, so -1, -5, 3 times 3 -1, 2 equals the modulus of both of them, so root 35 times root 14 times the cosine of the angle that is between them. If you use your scalar product and multiply these two guys together here, you get 8. So we end up with 8 equals root 35, root 14 cos of theta. What it's sort of worth having a kind of an understanding of is what the 8 is representing. It's kind of like what the length of one of the vectors is when it's projected onto the other vector. So if I take my vector b here and then I projected it in the same direction as n, it would have a kind of, and I multiplied the two lengths together, it would give me this number 8. If you ended up with a -8 there, what you might find is like you're getting the direction of one of them kind of going in the opposite direction to the other one. So a negative means that you might get the two vectors going in opposite directions, and we might actually be finding an angle popping out here, but we haven't got that in this case, so I don't think you're going to get that. So for this one, let's continue. If you solve this, we get, let's do it in blue, we get theta equals 68.8. Because it's a show that, I might have needed to show a little bit of extra working. In fact, maybe it would have been worth me showing this. Cos theta equals 0.361 ... We will continue because I haven't quite finished that. I found this green angle, but I want the angle between the plane and the line. So to get that angle there, we're going to do alpha is, well, it's just 90 minus 68.8. That's 21.2. For the last bit, find the coordinates of the point x. So if I take the vector here, vector equation of the line, our point in space is dictated by this 7 minus lambda for the x bits, 3 minus 5 lambda for the y bits, and then 3 lambda minus 2 for the z bits. So that is the x coordinate. That bit there is the y coordinate. That bit there is the z coordinate. If we go up to the top here, where we've got our equation for the plane, right at the top here, we now have some different values for the x, y and z coordinates. So here we can put in our z coordinate, our y coordinate and our x coordinates. So we will do that. We get 3 times the x coordinate, which is 7 minus lambda, plus, then it's, oh no, sorry, it's not plus, scribble that out, it's minus 3 minus 5 lambda plus 2 times 3 lambda minus 2, and that equals 10. If you sort this out, you will get lambda equals -1/2. We haven't quite answered the question because we actually want to find what the coordinates are. So with that lambda, you're going to substitute it in here where it says lambda. You should get r equals 7.5, 5.5, and -3.5. I haven't quite finished because I haven't actually answered the question. The coordinates are 7.5, 5.5, and 3.5, because you've left it as a position vector if you leave it in this format. Now, on the next slide, if I jump forward 2 slides, there is an exam question. I'll just pause on that one. And if I skip to the next slide, there's the mark scheme for it. This one's slightly different to ones that the WJC might ask. It's an Edexcel question. On the next slide, again, I think it might be an Edexcel question, but it's still relevant. This one has the vector equation of the plane in a different format. And if I skip to the next slide, there's the mark scheme for it. I will finish there because it's just coming up to the end, and I'll hand over.
Thank you very much, Mr. McMillan. A very useful session there, I'm sure. All the resources and recording of this session will be available on the Catalan Cymru website for you to watch again, should that be the case. But for now, thank you very much for joining us.